Good afternoon. My name is Akshai Runchal, and I'm going to talk about CFD, past, present, and what we see in the future. Today is the 15th of August, which is a very auspicious day for Indians. This is the day of independence for India. So here's the summary of my talk. I'm going to talk about what is CFD, how did we get here, what can we do with it, and of course, where are we going next? So let's first consider what is CFD. We inhabit fluids and fluids inhabit us. We're surrounded by air, and 2/3 of the earth that we live on is water, and 2/3 of the human body that we have is fluid. So what CFD does is it predicts the behavior of fluids, plastics, and deforming solids. CFD solves the most complex and interesting problems we face. CFD is very challenging. For me, it has been fun for the last 50 years, and I hope it is for you. The physical world we live in can be roughly divided into solids and fluids. Solids, in the absence of any external forces, retain their shape independent of the ambience or surroundings. Fluids, on the other hand, flow to conform to their boundaries. Liquids form a visible free surface and may or may not fill the containment vessel, whereas gases completely fill the containment vessels and have no visible surface. There's a special form of gases which is ionized. So this is where the gas particles get dissociated, molecules get dissociated and charged. In reality, there are no solids. Solids are just fluids at rest. All solids deform, and the significantly deformable ones are called plastics. There's a continuous transition of matter between solid, liquid, and gaseous phases. So what is CFD? Here is the essence of CFD. I'm going to discuss the finite volume method. If we take any arbitrary control volume, delta V, which is bounded by a surface, and the surface normal is defined by the vector n here. So the essence of CFD is that the rate of accumulation in this volume is equal to the net influx to the surface plus net rate of generation. Nothing else can happen. So CFD is really very simple. It's like keeping a balance of something, like the balance of your money in the bank. Don't be overwhelmed by the complex equations. After all, your teachers have to earn their salary, so they have to show you all those complex equations. For me, what's been important is always think physics, not math. And I think that's where an engineer's intuition will come in. Once you think of the physics, what should happen. If you can manage your bank account, you can do CFD. So here is the general balance equation. For any property phi that flows, the accumulation of that property with time d phi dt over a control volume is given by the first term. The flux of this property coming in at the surface, money goes in, money goes out, is given by this specific term, which is basically the rate of movement multiplied by the surface, normal of the surface. And finally, there is the source term, which is like the interest or the bank fees. And if G is the source, then over the control volume, we can take an integral. Now, if we use Gauss theorem, this equation simplifies into d phi by dt is minus del dot V times the property phi that is transported plus the generation term. What of the contribution that Imperial College Spalding made was to say that let's generalize anything that can move. Anything that can move can be described by this general transport equation. The storage, the change in the storage is given by the d by dt of the phi quantity. Flux is of two kinds. Advection is one which moves with the velocity of the fluid. That's given by this term, d phi by dxi, velocity times the property and the coefficient. And the second type of flux is diffusion, which is due to the molecular motion, which is kind of a Brownian motion, which can't be defined at the macro continuum scale, and therefore is defined in terms of diffusivity and the gradient of the variable. Things flow from higher gradient to lower gradient. And then, of course, there are source terms and then the sink terms. So this equation expresses the balance of any property that can move. Of course, this is in a continuum approach. Fluid, heat, mass, electrons, cars, humans, fishes, anything that is present in large enough numbers to be considered a continuum. So why do CFD? Well, to understand the physical biological world, we need CFD. As I said, man inhabits fluids and fluids inhabit man. 71% of the Earth's surface is water. Human body is 2/3 fluid. We are immersed in air, another fluid. Whatever solids are there in Earth or our body are mostly deformable. Okay, you know that because a child grows into a man and all the bones deform to make him into that. So every human endeavor involves fluids. CFD applications span human existence, industry, environment, human body, biosphere. What can be done with CFD? Well, as I said, it spans human existence, industry, environment, and everything. So CFD tools are critical to aerospace, energy, transport, national security, engineering design, food and chemical processing, consumer electronics, environment, disaster management, life sciences, earth sciences, astronomy, virtual reality, animation, you name it. CFD can do it. So with that preamble, let's look at the past. It's a bit of a personal perspective, a bit of a subjective history. I grew up in the remote hills of Himalayas, shown on your right here. My house is just about there, next to these dishes. I never dreamt of participating in the birth of a new branch of engineering science. I thought it was more likely that I'll grow or I'll have a few sheep and graze them around. We were 6 adults and 11 children in this remote hamlet, which we thought time and God had forgotten. But I was lucky enough to witness the emergence of CFD at Imperial College. McLeodganj, my hometown, became the home to the Dalai Lama. It became a symbol of rejuvenation of Buddhism, a cause célèbre for human rights, and a prominent place on the political maps of India, China, and the US. I'm a lucky man. I was at the right time at the right place. I invite you all to come and visit me. Just go to the web browser you have, type in McLeodganj or Dharamshala, and you'll see my town. So let's look a little bit of the history of what contributed to CFD. Well, like any science, Newton said, I stand on the shoulders of giants and therefore I see far. Well, that is true of every branch of science. CFD also stands on the shoulders of mathematicians who went before it. Those mathematicians developed the tools that would later form the foundation of CFD. Finite difference method, of course, numerical analysis, matrix theory, couple of minimization principles, the Hamiltonian and the variational methods. These all contributed to the CFD or helped CFD when it came around. This happened over the previous couple of 100 years, well before the 1900s. And then Richardson and Cura and Friedrichs made some seminal contributions to the theory of numerical methods, which CFD could exploit. Then Cura in 1952 made a very important contribution by introducing the concept of upwind differences. This all happened before electronic computers, or more or less before electronic computers. There was some CFD before that too, believe it or not. Thom in 1933 derived a finite difference solution for the flow past the cylinder. So how did he do it without the computers? Well, he used human computers. He used what he called urchins. These were street children that he picked up, paid them for every multiplication, addition, and subtraction, and used a stream function vorticity method with a central finite difference to derive a stable solution for flow past a cylinder at a Reynolds number of 50. Southwell developed a very important technique called the relaxation method, which is still used today for the elliptical problems to speed up convergence. Allen and Southwell in 55 used these technologies to derive the finite difference solution for flow past a cylinder up to a Reynolds number of 1000. One of the new innovations they introduced was to employ conformal transformation. Flow past a cylinder is essentially an infinite domain. So what they did was they used a tangent-based transformation to reduce to a finite domain. Other people who were active during this time before computer were Tom and Apple, Kawaguchi, Simony. They also made important contributions. The birth of CFD happened in lockstep with computer systems, and it can be attributed to two brilliant scientists. Frank Harlow at Los Alamos, who started in the late 1950s. The first computer at Los Alamos arrived, IBM 701, in 1953. Brian Spalding at Imperial College, he started in the mid-60s. That's when the Imperial College saw its IBM 7090 in 1962. The interesting thing is that both worked independently, didn't know much about each other's work till both had almost done it. But it was Spalding who made CFD a common and popular tool for engineers. Harlow was at a national lab, Los Alamos, Manhattan Project, Defense Lab, secret work. He was not, primary interest was not to commercialize or, or export his technology. So at Imperial College, CFD emerged in the mid-1960s, but there were some important things that went before that. This was done by Spalding's group, and these are the things that happened. Spalding had already derived over a period of time, over a decade or so, a common format for fluid flow, heat transfer, and mass transfer. He had also derived a universal, unified theory of boundary layers, jets, and wakes. Okay. More important, he had done an extensive in-depth survey of the experimental data to determine universal empirical constants needed to account for turbulence. Then he had also made innovative contributions in theoretical and experimental combustion, including evaporation burning of droplets. These led to the B factor and the Spalding number that is used today. These developments would prove crucial in leading to the CFD and the developments that came to be known as the Imperial College approach or the finite volume method. So landmark in the FEM was like this. In 1964, Suhas Patankar, who was a fresh PhD student, built an integral profile code. Integral profile, before that, boundary layers were solved, or specific boundary layers were solved by using an analytical profile with some arbitrary constants, which was assumed or called a similarity profile, and it was put into the equations. It led to certain constants which were fitted by boundary initial conditions. What Patankar and Spalding did was they simplified this profile and generalized it by saying we can build any profile by piecewise linear segments. So this was called the integral profile method. It was not quite finite differences. It was an analytical profile made with piecewise linear systems. Nonetheless, it led to algebraic numerical solution like the finite difference scheme. However, this method could not be used for separated flows or flows with high streamline curvature or strong pressure gradients. So Spalding asked Runchal to use the finite difference method for stream function and vorticity, and Micha Wolfstein to use the same or similar technology for impinging jets. So in 1966, Runchal and Wolfstein combined their work to develop a finite volume code for two-dimensional high Reynolds number flows. 1969, this was published in the first book on the CFD that used the Imperial College approach. In 1972, the next development came when Spalding and Patankar developed a three-dimensional velocity profile primitive variable code that was called SIMPLE. And this revolutionized the use of Imperial College technology. So if we're looking at birth of CFD, I would call 1962, nine at the year. That is when Spalding had realized the importance of the commercial potential of CFD. He arranged a post-experience course at Imperial College, which targeted both academic and industrial communities. And he incorporated a commercial company, the first commercial company in CFD called CHAMP. Also, the first book on CFD, Heat and Mass Transfer in Recirculating Flows, was published by Academic Press. The book, unlike the focus on intellectual property of today, this book contained the full computer code for 2D Navier-Stokes equations called ANSWER, which we freely distributed to anybody who asked for it. It was also in the book, of course. So Spalding had a strict rule that all joint publications carry the names in alphabetic order. So that is how the authors are listed in our book. Actually, David Gossman was the compiler and the editor of individual contributions from Spalding, Runchal, and Wolfstein. And Sam Pun was the one who took over the ANSWER code and its further development and distribution, because both Runchal and Wolfstein were leaving, one for Israel and one for India. Another technology, parallel technology, developing about the same time, a little later, was the finite element method for fluids. There were two pioneers, Argyris, primarily structures, and Zienkiewicz, who went into the fluid dynamics field. They were both close by, Argyris at Imperial College and Zienkiewicz at Swansea. We met with them, had discussions about FEM and FVM. FVM was originally developed for structural applications. So in early days, in those days, when we were working on it, it was not suitable for high Reynolds number flows. They had not yet developed the technique of dealing with discontinuous profiles. Also, it lacked a clear theoretical basis for fluids because the Hamiltonian, the minimum energy, does not exist for nonlinear systems. But in my opinion, a bigger drawback was that finite element method uses global error minimization even today. There are many systems, such as combustion, where a small change or small error can lead to orders of magnitude larger error in some other thing, like a small error in temperature can lead to a big error in reaction rate. So local mass balance can be very important for these highly nonlinear systems. Since then, both have techniques have appropriated, borrowed, stolen from each other, and today the differences are semantics. But on the practical side, most current commercial codes use finite volume method. So in summary, and one interesting fact was this in summary, that CFD name was not coined by either Harlow or Spalding. It was first used by Pat Roche in his famous book called Computational Fluid Dynamics. And it was the IC approach that led to the development of CFD to problem of interest to engineers, primarily because it provided a uniform framework for flow, heat, and mass transport. And our focus was on physics, things engineers could measure, rather than on mathematics. We were concerned also with the engineering practice. If we did not understand all the theory that was behind something, such as behind turbulence, but we knew enough to get the work done, we did it on the belief that the proof of the pudding is in eating it. And so we could use an approximate model. Today's commercial code, as I said, trace their origin to the work done at Imperial College. Let's look at the present. The situation at present is that CFD is one of the most powerful tools in every field of human endeavor. It's pervasive, as I said, in industry, economy, environmental existence. And I've given you a long list before, and here it is. But basically, you name it, and CFD is used for it. I'm not going to dwell on it. You all know CFD. I'll just give a few illustrated examples. So here is an example from environment and disaster management. This is a hypothetical tsunami that is going to hit the coast of Monaco. There is the Monaco harbor there in front of you, like a square part. And here is the tsunami coming. And we want to know what are the high waves and the high and low points of the waves. Where do they hit? How do they flood? How do they retreat? And we can do that, of course, with CFD. There is nothing we can do in real life. When the tsunami comes, the only thing you can do is try to deal with it and escape. This is another case of a tsunami being simulated. This was the Sumatra Tsunami of 2004. And we performed a simulation of that tsunami in hindsight to try and match what was observed in terms of flooding and water heights at different points on the coast of India. And the interesting thing here is that the impact of the tsunami even went to the west coast and the Arabian Sea, thousands of miles away. This is a case from the environmental impact point of view. This is sewage, which is discharged into the harbor of Dieppe in France. And so the question is, what happens to this sewage? What are the residence times? How does it go? How does it return? Where does it go? So this can all be simulated with CFD today and increasingly done so. Let's look at the human body and pharmaceuticals. Here is an example of the drug diffusion in rat brain. As you know, blood-brain barrier is a very important barrier, and we don't fully understand what goes across this barrier and what doesn't go across this barrier. So sometimes the option may be to inject drugs directly into the brain. If we do, how fast do they travel? Where do you go? What are the concentrations? These are the kind of questions that we've done. So this is the model of a rat brain that was actually studied. The poor rat was, of course, dissected at the end of that and matched with the data, and it came out quite reasonably well. Here is a case more pertinent, that of COVID. And the common advice is stay 6 feet away. Well, this shows that that is not always correct. You have two scenarios here. The inlet of the flow is at the ceiling. The outlet is either on the ground on one of the walls, or it's again in the ceiling. Both scenarios occur in practice. And you can see that if inlet and outlet are the ceiling, the flow paths go back to the ceiling and engulf a recipient to the other end. So the basic message should be that look at the airborne transmission. It is possible, and it happens. There's some engineering applications. It's a flow around and inside a car. Outside the car, it's used to design the body so the drag can be minimized, fuel consumption can be optimized. Inside, we want a comfortable temperature for the driver and the patient and his companions. So here is a case of a study of a body skin temperature distribution on the contact surfaces inside the vehicle. This is the case of a wind turbine. Wind turbines are playing an important role in renewable energy, and how many turbines to place, how far, at what density, what speeds, and how the energy should be generated so they don't interfere with each other is an important question. And this question was studied through wind turbines. The case of a comparison between a numerical simulation and a MAT astronomical body on the right, and it's a very well-studied case of a spiral stellar potential driven shock and star formation in a galaxy. So this is the case of the electronics. Every electronic component today is limited by the thermal energy that can be dissipated. And this is the case on the left of that of a circuit board, on the right of a cabinet, which contains electronic components and how to optimize them. This is gas turbine engine is one of the most complex engineering equipment there is. And no turbine is designed today without doing extensive CFD. Actually, the mode today is that no metal is cut till a CFD solution has been obtained. And of course, then once the metal is cut, you still have to test it in real life. So let me move to the future. So firstly, before moving to the future, what are the challenges on the horizon that we must overcome? CFD today is a combination of three components: science, art, and guesswork. Science is in the fact that we know Navier-Stokes, Boltzmann, thermodynamics equation, which is physics with well-defined and accepted mathematical basis. Art is in designing an efficient system because we have limited computer resources. What is the most efficient system? What is the most efficient algorithm, matrix solver, things of that nature. Now we come to the guesswork. The fact is that we do not understand many aspects of real fluids. Actually, I would say we understand less than we pretend to. Most of the fluids, real fluids, we do not understand. There's very poor scientific basis. We only have hypotheses or empirical data. So let's look at the lack of knowledge challenge. Most important is poorly understood physics and chemistry. Let's take the case of reaction mechanisms. Take hydrogen and oxygen. It can be defined as a one-step reaction, H2 plus half O2 H2O, or it can be a 50-step reaction, or maybe even 100-step reaction. H2 dissociates into H plus H, O2 into O plus O, HO combined to form HO. So all these things happen. There's reverse reaction, forward reactions, intermediate reactions happening all the time depending on the operating conditions. And what is it we're looking for? Are we looking for the detail of what's going on? Or are we looking for an end result? Complex hydrocarbons are mainstay of energy economy. Hydrogen and oxygen is simple. Complex ones, these hydrocarbons, we do not understand, I would say, almost at all. Okay, we know their, how many carbon and hydrogen atoms they have, but beyond that, we don't know their reaction rates. We don't know the fluid properties often, except for some very well-known studies like methane and all that. But most of the energy today is not generated by methane. So what is the physics and chemistry of blood? Do we understand it? No. Is it Newtonian? Maybe. What about cerebrospinal fluids? Well, again, the same story. Okay, we don't understand the physics or the chemistry. The other thing we don't know are many of the mechanisms and processes that affect as the fluids move through a system. Well, often there is interaction between reactive, magnetic, and chemical processes. We don't know that. How does a molten rock or metal behave at very high temperatures and pressure, like in the core of the earth? We don't know. How does the liver manufacture all those chemicals? We don't know. How does the blood-brain barrier work? We don't know. There are two kinds of uncertainty. One is lack of knowledge, We call it epistemic uncertainty. So most practical flows are turbulent, for example, but we don't understand the turbulence chemistry interaction. So there are too many models, each with limited applicability and none that we can rely upon 100%. We don't have other physical inputs such as diffusivity, reaction rate, etc. And that is another uncertainty. There is a second kind of uncertainty called aleatoric uncertainty. That means some variable by nature are unknown, random, or stochastic. For example, initial and boundary conditions. Take an atmospheric case or the case of simulating an ocean flow in the ocean. Well, the initial and boundary conditions are very highly stochastic. They are functions, complex functions of many variables, and we almost certainly never know them exactly. Sometimes we don't even know the domain of influence. If we are simulating a part of the ocean or part of the atmosphere, or let's say flow over a city, how far should we go? We don't know. When these uncertainties combined, and there is more than one, we call it a multivariate, multiple uncertain inputs. Now problem becomes an order of magnitude more difficult when multiple variables are stochastic. There is no good mathematical methodology to do that. Certainly no analytical methodology has been developed. Other challenges involve multiple coupled phenomena. For example, multiphysics is the norm or will become the norm. Almost all practical systems involve multiple physical phenomena, such as fluid structure interaction, combustion, which is heat plus fluid plus mass transfer, electromagnetic, which is Navier-Stokes plus Maxwell plus thermal equations. So this makes the problem, takes another order of magnitude complexity. Multi-phase. Phase change is very poorly understood. Even for water, which is one of the more easily understood phase changes, we have these tables, massive tables that define phase change, and they only define them with certain accuracy. Another problem occurs is when there are multiple fluids involved, flow of water, air, and immiscible oil, such as that in a typical groundwater situation where we are concerned with the impact of an oil that may have leaked into the ground. The other difficulty is multi-scale simulations. We may have simulations where we need both Navier-Stokes and Boltzmann. They may be discrete and continuum problems. We could have problems that go from nanoscale to macroscale. On one hand, we're dealing with the outer space where there is very little density of fluids. And then we're dealing with the inner where we go into the capillaries and the scale is very small. Another type of phenomena which creates problems for us is what I call the integro-differential processes. These are processes where practically this one kind of energy is coupled to every other point in the space. Thermal radiation is a good example where each point in space radiates to the others. Aerosols, droplets coalesce, droplets break down, droplets move at different speeds, and things of that nature. Soot sprays, particulate flows are good examples where we need to do an integral over the whole space or over a part of the space to understand what's going on. Other challenges that face us are the change in time and space of our own working space. Take, for example, the folding and flapping of wings or aircrafts, birds and aircrafts, okay? Heart veins dilating and pulsating. These create problems for us because we have to change the domain in time and space. The other thing is sometimes we're required to do simulations over a space which goes from meters to thousands of kilometers. For example, the air pollution behind a building may be impacted by local and global airflows. Then there are processes which couple with disparate timescales. For example, take combustion. The reaction rate for one reaction can be femtoseconds, and another reaction may be at the level of seconds or sometimes even hours. Time scale for combustion is in seconds, femtoseconds, or milliseconds, and that for the flow is in minutes. Fluid structure information. The information speed for the structures is sonic. That for the fluids is based on its velocity. So which one would be the norm? Which one would govern? There are some specific challenges that face. One of those is the CFD algorithms. After 50 years of CFD, we still have no satisfactory method to deal with the convection terms in the equations. The flow regime changes from elliptic to parabolic to hyperbolic because of interaction between convection and diffusion terms. Diffusion is a second order process. It is linear in nature. Convection is a first order process and leads to non-linearities. No good or robust, accurate scheme that combines these properties. Many schemes have been devised, none fully robust and none accurate under all good conditions, practical conditions. Let's take another solver, that of matrix solvers. The governing equations, the way we solve them, they admit multiple solutions. Turbulence is a good example. Computational methods linearize the nonlinear problems. They cannot solve nonlinear problems, so we linearize them. Matrix solvers can only solve linearized equations. So all these methods leads to large matrices of large number of unknowns. They may have millions of unknowns and millions and trillions of computations involved. No satisfactory matrix solver exists for such applications. It's only trial and error, and that's what we depend on. So we need robust, accurate, and economic solvers that produce the solution, or we want to go away to methods that do not depend upon matrix solvers. Another challenge that is occurs is that of computer architecture. Computer architecture today is evolving towards parallel and cloud computing systems. CFD methods have not evolved to optimize their use. They were primarily developed for sequential computers or few parallel pipes, 10, 15, 20, that kind of thing. Many CFD methods are implicit or partially implicit. Therefore, it's not possible to fully and efficiently utilize the computer resources of a cloud computing system. The methods today do not scale linearly with the processors. There is no method I know of that would scale linearly if you increase the number of processors to 100,000. If you do so, the communication time required may even exceed the computing time. Switches are much slower than CPUs and GPUs. So we need better management methods for cloud and parallel computing and computational methods to optimize them. So let's look at the future now. What is in store for us? Well, CFD, the future, the codes as we know them today will disappear. That's at least my belief. They're too cumbersome to use. There's a long training period required, months, quite often, if not years. No checks and balances for reality. Most of them give you a solution. You don't know if it is accurate, if it's physically possible. There's poor overall reliability for critical applications. I would not fly an airplane today, and nobody would recommend flying an airplane today that is purely designed with CFD. Okay, I'll take a bet from anyone who wants to do that. Today's codes are very resource intensive. We are always complaining we don't have enough resources. So we need CFD of the future that has better use of computer resources, architecture, algorithms, and solvers. Also, as I said, we need better science and less guesswork. We need better models for turbulence and other physical processes. We need much better models for dealing with stochastic phenomena, which is very important for many applications. So where we are going will be machine learning models, which will have the CFD knowledge built into them. These would be the digital twins, or what we call the physics-informed neural networks. And these will then be combined with what I call engineering virtual reality, where you'll be able to move inside an aircraft engine, or you can move behind a waterfall and look all around you and move around and see what is happening to the flow. Here is a crude attempt at what the future may look like. Here is a tsunami that is actually imposed on the topology of city of Cannes. So we could see how much flooding occurs, where it occurs, and how to define a strategy so the damage is minimized. So you can see the water going past the buildings. And if you look in the far right up there, you will see the water flooding a whole low-lying area, which is near the, I believe it's the village of, it's the Oahu, but I'm not absolutely sure. Okay, so this is what the future of CFD is, when we will actually, when we do a disaster simulation, such as what happened in New Orleans, we could actually simulate what's going to happen, take steps to avoid the disaster that did occur. So what is machine learning? Machine learning is basically neural networks. When we have multiple layers, we call them deep neural networks. They've been successfully applied in many fields: image processing, natural language, speech recognition. They can deal with highly nonlinear problems. It can also be used to augment knowledge of phenomena that we don't understand, such as if Rand's model doesn't work for some particular case, can we add a term to it? Can we learn from the data and add an additional term that solves that problem? So physics-informed neural networks basically embed the Navier-Stokes equations into a machine learning model. So basically, the input of boundary conditions or flow conditions or equipment conditions are fed into a neural network. There is some criteria based upon an output is obtained that is plugged into Navier-Stokes equations, and then we see if the Navier-Stokes residues are residue criteria satisfied, if they're small enough. If not, we go back, retrain our neural network till we get that condition satisfied, and that is what becomes a physics-informed neural network. So CFD, machine learning and surrogate models, is where the future is. So what happens is we combine CFD with machine learning, and it improves the modeling effectiveness. For example, we can use this to augment turbulence models with additional terms. We can use it to get new constitutive laws, new models for multi-phase flow or combustion. We can replace the laminar flame-light model with a better model from machine learning. The training data for that can come from CFD itself, experiments, and real-time data. So the main advantage of ML is that it combines these. So PINN is a good vehicle for developing these surrogate models. A surrogate model is basically nothing but just a fast and accurate representation of physical system. Very useful in situations where CFD is very expensive and resource intensive. Then the surrogate model, when combined with other things, as I will show, is basically what we call a digital twin. And it can be used then to design optimization, inverse problems, uncertainty quantification, and of course, for many other applications. So let's look at the digital twin. Digital twin is a very promising area of the use of machine learning and CFD. It's a digital representation of a device or a process, which gives up-to-date real-time representation. It's a data-driven model, which is enhanced with PINN, Internet of Things, sensors, and any other information we may have about that problem. So this sketch here shows basically the digital twin, where everything is going through the Internet of Things, and the PINN model output is being optimized till we have a satisfactory system. We put in the sensors there, the information from the electronics goes in there, all the network information can be plugged in, the logic of that can be modified or trained, and we can use the information from the cloud, and we can store it in the cloud, and all those would then become a digital twin. And what happens is, it's a comprehensive model of a complex system that produces tabulated or analytical analog of the device or process. Here is an example. Look at this automotive cooling system. It's got many components. As you can see, there are pipes, there is a pump, there is a fan, there is all kinds of things that are, there is electronics, there is a radiator, all things are going on. So what is commonly found is the design of the pump, simulation of the pump basically consume disproportionately large amount of time that I'll get into in the next slide. Our real objective here is to design the cooling system, not the pump, okay? So multi-phase CFD simulation of pump is very expensive. So what do? What we do is first look at it, why simulation of pump is expensive. It's expensive because pumps require sliding meshes and multiple rotating frames of reference. Okay, pump is moving, blades are moving, flow is moving through it, there is a stationary part. So then what happens is there's a two-phase flow due to trapped air bubbles in the cooling system. Then large air bubbles break up into small bubbles passing through the pump. Usual pump models cannot capture this, and to go to very detailed model increases the time and makes it very uneconomical. So multi-phase CFD simulation of the pumps are therefore computationally very expensive, and we cannot afford to embed them in global CFD simulations. So the solution is to replace the pump with its digital twin developed by a machine learning model, which will give us a lookup table that simulates the IO pump. So global CFD solver will then use digital twin to replace the pump. Just look up a table rather than solving for the pump and economize on the computing resources. Here is how we did it. We basically took the pump, did multiple simulations under different inlet and outlet conditions, generated the training data from that. Then we put it into a machine learning model, and we improved it with the empirical data as it was available. So the summary of a digital twin is you basically perform CFD simulations for the component of interest. You call neural networks from the CFD solver. You combine with the empirical data. You combine with Internet of Things. You develop a digital twin. Then you remove part of the mesh representing the component from the global CFD model and replace it with a digital twin. So in summary, digital twin leads to accuracy plus speed up. So as more demands are being placed on CFD analysts to simulate design conditions, simulate off-design conditions, anomaly detections, different feature mates, multi-physics CFD will become the norm. And of course, we'll begin to combine CFD with structures, electromagnetics, vibrations, acoustics, systems, etc. The future norm for high fidelity CFD simulation design will be to combine it with physics-informed networks, deep neural networks, and digital twins and surrogate models. So here is the future, in my opinion: CFD modeling with PINNs, deep learning, digital twin, and don't forget virtual reality. I want to be able to walk into my system, look all around, just like walking into a house and looking into every room from every angle. Thank you very much for your time, and I'm open to questions.